My name is Dr. Shane Reeder, and I'm a legal epidemiologist. Like most epidemiologists, I use risk factors to evaluate outcomes, but instead of looking at biological risks like genes or diet, I look at local law and policy. One question that's important to me is, do these harm reduction laws, called 911 Good Samaritan laws or overdose bystander laws, save lives from overdoses? These laws protect people from criminal consequences if they're reporting drug overdoses, even if they have drugs on them. But the laws are really different across states. They're so different, I created my own policy surveillance dataset to describe all these differences. I sorted all the variables into 4 categories. Breadth variables are the criminal offenses and agents who may receive GSL immunity if they call 911, broader laws being those that protect more people. Burden variables are the obligations the Good Samaritan must meet to receive immunity. Strengths are variables that describe the nature of the immunity, what kind of protection you get. And exemptions are variables describing circumstances where immunity is revoked. Here's the challenge. First, states are in the dataset multiple times if they've amended their laws, but let's put a pin in that. More importantly, I have more than 80 variables, and most of them are binary, just a 0 or 1 to indicate the absence or presence of the feature. Ultimately, I want to plug this into a linear regression, so I'll need to do some dimension reduction. You see, every variable in this dataset is a dimension, just like we can have dimensions in space. If there were only 2 dimensions, we could plot them in space and calculate the distance between each pair of observations using the distance formula. If we have a 3rd dimension, we extend the distance formula like this. Well, here's the fun thing. We can extend the distance formula for as many dimensions as we have variables in our dataset. So first we filter the dataset to just the first version of each law passed by a state, the originally ratified text. Then we calculate the distance between every pair of state law observations by extending our distance formula like so. That leaves us with a distance table, like a table of distances between cities in the back of an old road map. Just like we can reconstruct a map from a table of distances, we can reconstruct a map of GSLs, now in 2 dimensions instead of 83. And it looks like this. Each dot represents a state law, and closer laws have more dimensions, or variables, in common. Remember that every variable is categorized as either a breadth, burden, strength, or exemption. Well, I can add up all the variables in each category to score each law. And when I do, we see that laws with great strength wind up over here, burdensome laws are down here, and laws with lots of exemptions are pushed to the outside. Also, look at this. Certain constellations of laws all share certain features. All the laws in this zone, for instance, protect a Good Samaritan from probation violations. These states here may still prosecute the person whose drug overdose is reported. Taking this map, I can conduct a cluster analysis to divide all these laws into groups. I get 5 of them, which I named minimal, moderate, narrow, rigorous, and strong laws. To better define these groups, I had a supervised learning algorithm make a decision tree for me, sorting state laws into groups based on their variables. The 4 variables that best determine group membership are whether protection depends on how much fentanyl a Good Samaritan possesses, whether it provides protection from the filing of charges, whether they must cooperate with law enforcement, and whether they receive immunity for parole violations. Now let's unpin that states across time thing. We can use this decision tree to determine whether any state has amended their law sufficiently to change group membership over time. Massachusetts, for instance, changed from a moderate to a strong law in 2018 by adopting protection for probationers. This method has several advantages. Now I have a single reduced variable, group membership, that captures most of the variance in this giant dataset. It's atheoretical. We don't tell the data what's important, we let the data tell us what's important. And it accommodates all kinds of data structures, including this weird, highly dimensional binary data. Nowadays, we have so much multidimensional data that it's paralyzing. We have more alternate dimensions than we know what to do with. The lessons we've discussed here can help other policy scientists navigate that nth dimensional space as well. I encourage viewers to consider how policy surveillance data could inform their own research in the future.